Hello everyone, Mrs. Hanson once again, and our journey continues in Chapter 7. I know it is a very long, very challenging chapter, and I do encourage you to make sure you spend time with each and every one of these video lessons working for mastery. Now, of course, we're turning our attention to unimolecular reactions, both the SN1 and the E1 reactions, unimolecular. So when a tertiary alkyl halide is dissolved in a polar solvent that is acting both as a weak base and a weak nucleophile, for example, ethanol. Ethanol, of course, CH3, CH2OH, you'll see that abbreviated as ETOH, ethanol. It is a protonated alcohol, right? So what we're thinking here is that it's a weak nucleophile, weak base. Remember that weak bases are conjugates of strong acids, okay? And so ETOH would promote SN1 and E1 mechanisms. So here, for example, we have a tertiary alkyl halide. The alpha carbon, the carbon that's attached to the leaving group, the bromine here, is attached to three other carbon. It's called an alkyl halide, and it's a tertiary. So in a substitution reaction, think about the ETO and the actual bond here in a stepwise mechanism, stepwise because it's unimolecular. The substitution product will end up having an ether linkage, which is ROR, if you recall, and the oxygen then has been substituted where the bromine was. And of course, the elimination reaction involves the formation of a double bond, a pi bond. We're going to explore how this reaction mechanism occurs in both a substitution and the elimination product. And to be sure we understand what controls an SN1 and E1 mechanism versus SN2, E2 mechanism. So ultimately, we would like to be able to predict the mechanism and the outcoming products. Remember, primary alkyl halides and a strong nucleophile promoted SN2 mechanism. A primary alkyl halide did not have what we would call steric hindrance. And so we had a very polar bond where this made the carbon electrophilic and this guy here a very good leaving group. And so when your nucleophile, which was a strong base, strong nucleophile, would have an easy time attacking the alpha carbon, and the leaving group would then just leave. So that's a nucleophilic substitution where you would see where the bromine was, the nucleophile had added on, a substitution. And of course, we also saw that strong bases promoted E2 mechanisms. And if you had an alkyl halide, again, secondary or primary, even tertiary if it's a strong base, because the tertiary could then have beta hydrogens that it could also explore. So let's just say we had a bromine that is a tertiary alkyl halide, but we have a strong base, something such as, let's say hydroxide. You could see then that the beta hydrogen would be then proton transfer. We saw the bond collapse and the leaving group leave. So we just finished talking about that sort of chemistry, knowing that you end up making a double bond for elimination. And in substitution, primary alkyl halides, strong bases, strong nucleophiles, we can promote SN2 reactions. Now, let's consider the unimolecular reaction. Unimolecular means the rate determining step involves just one molecule, not bimolecular where two molecules collide in a concerted mechanism. But here we have a stepwise mechanism where the rate determining step is the leaving group leaving. So here we have a tertiary alkyl halide, and as long as that alkyl halide is on the carbon chain, the reaction cannot proceed. The leaving group must leave in order for a carbocation to form. And this should be one word, carbocation. is truly what we would call an intermediate in this reaction mechanism. And we see the carbocation with its sp2 hybridization, that it's trigonal planar, that it lies exactly flat on the paper there. So we could see a top side or bottom side attack when we consider stereochemistry. But since the leaving group leaves and initiates the entire stepwise fashion, it's said to be the rate determining step. And therefore the kinetics would rely only on the concentration of the alkyl halide, which we refer to as the substrate. So this step determines the kinetics of the reaction. The leaving group must leave and form the carbocation, and then we would have either SN1 substitution occur or E1 elimination occurs. So the rate of the substitution reaction in a unimolecular pathway depends upon how fast the leaving group leaves. The better the leaving group, the faster the reaction. So the loss of the leaving group initiates the rate determining step. Thinking about forming a carbocation, we want to remember considering how stable is that carbocation. In a previous chapter, we talked about the stability of a carbocation increasing with the more substituent branches so that it had kind of a delocalized stabilization from the nearby methyl groups. Notice in this example, we have a tertiary carbocation, which is, of course, the most stable configuration. The carbon that is electron deficient, notice that it's missing its fourth bond, and that's why it's carrying a positive charge. When the leaving group leaves, it picks up its electrons, and you literally form the bromide negative ion. So there's your leaving group. The bromide leaves, and it creates only 3 bonds on this alpha carbon. 3 bonds leaves that carbon electron deficient, making it a positive carbocation. It can be stabilized across more carbons. So that's why a tertiary carbocation is very stable. And remember, if you had a secondary carbocation, that would be less stable. And of course, a primary carbocation, where we have only one other carbon, is the least stable. And I would start to suspect that a primary carbocation would not promote SN1 reactions. A leaving group just won't get up and leave if it's not stabilized in a carbocation. And remember, we'll talk about this in a little bit too, but remember that there are some shifts available, either hydride or methyl shifts, to help create a more stable configuration as well. So all of these things are considered when the leaving group leaves. In order to promote the leaving group to leave, you have to have a good leaving group, one that can stabilize the negative charge, and you have to form a carbocation that can handle the positive charge. So notice 2 ions form by the loss of the leaving group. One of those ions is the carbocation, and the other ion is the leaving group. Alrighty. Then, after we've had the leaving group leave, step 1, the rate determining step. The leaving group is now the bromide, it's gone. Notice that we now have sitting on the arrow the solvent. Now in this case, the nucleophile is exactly the same as the solvent that's running the reaction. When the solvent acts as the nucleophile, it's simply known as solvolysis. There is not a separate nucleophile as in the SN2 E2 mechanism. The solvent itself is the nucleophile. Or in elimination, the solvent would be the base. Notice now this oxygen-rich, this is a very electron-rich area on the oxygen. Now we'll go and form a bond, and notice that's what happened. Now this carbocation has a 4th bond. So the ETOH, which is ethyl alcohol, just keep in mind what that looks like. It's a 2-carbon chain with an alcohol group. The 2-carbon chain is attached to the carbocation carbon, and this is now what we call a protonated alcohol there. And so notice that right now that's a positive charge on the oxygen simply because it has a formal charge of +1. So at this point, that's an unstable configuration for that oxygen. The solvolysis still continues. The solvent then in the next step undergoes a proton transfer to create a more stable arrangement on this oxygen. So it will abstract the extra proton that was originally on the alcohol. This bond collapses and makes dots on the oxygen, and so no more formal charge on that oxygen once that next step of deprotonation occurs. So here, OET, think about what that means structurally. You have an oxygen, then a 2-carbon link. We have formed an ether linkage in this substitution reaction. So, lots to digest. Here we had the rate determining step being the step in which the leaving group leaves. Step 1, the rate determining step, the leaving group leaves, that forms the carbocation. Step 2 is a nucleophilic attack, where the solvent attaches to the carbon. That is the alpha carbon. It's electron deficient. It's missing its 4th bond. We now have an oxonium ion. As I had suggested, notice that this oxygen carries a plus formal charge. That's an unstable configuration. So therefore, we need to deprotonate. And to do that, the solvolysis continues. The solvent then reaches out for that proton and deprotonates it to create the ether linkage as the substitution. So notice substitution occurred. We turned a bromide into an ether linkage through an SN1 mechanism. It is a multi-step mechanism. SN1 is multi-step, where the rate determining step is unimolecular. The leaving group leaves. SN2 is a concerted mechanism because we had bimolecular collisions. All the bonds broke and formed at the same time. Since SN1 is multi-step, think about what its kinetics would look like. Multiple steps involves multiple activation energies. We said step 1 is the rate determining step. So you can see the rate determining step would have the highest activation energy. From the reactants to the top of the energy barrier, you have the activation energy. And so remember, at the top, you have transition states. And we showed those in a bracket with a double dagger, a transition state. The intermediate that forms is at the bottom of that first energy hill. This carbocation was an intermediate. It is formed and then immediately gets consumed in the next reaction. You would have a next transition state at the top of the energy hill for step 2, double dagger there for the energy transition state, and then yet another intermediate. The intermediate is the protonated ether. That's an unstable configuration. It's called an oxonium ion. The positive charge on the oxygen is an unstable configuration there, and therefore we need a next step to deprotonate that ether linkage, and that's what the solvent does again. The solvent deprotonates the ether linkage to finally create our ending product. So we had step 1, step 2, step 3. Notice that shaded in blue, you have substitution reactions, and shaded in purple here is acid-base chemistry. That is a proton transfer. Step 1, substitution. The leaving group leaves and forms a carbocation. Once the carbocation forms, the solvent itself acts as the nucleophile and creates the substitution, the protonated ether. The formal charge on the oxygen needs to be alleviated, so we deprotonate that. And the last step is acid-base proton transfer. So the E1 mechanism, we just studied substitution, the E1 mechanism again attacks the protons of a beta hydrogen. Here is a tertiary alkyl halide. The rate determining step says I'm going to sit there until the leaving group leaves. The rate determining step says the leaving group has to leave. And when it does so, it picks up its electrons and forms the bromide anion. So here we have the carbocation intermediate. So far, exactly the same as the SN1 mechanism. So now all of a sudden, if the intermediate, if the solvent is ETOH, and remember, if it acts as a base, we undergo elimination. If the solvent acts as a nucleophile, we undergo substitution. So that's just the difference here and these are competing reactions. So if the solvent goes for the proton in the beta position, you form the alkene as the elimination product. If the solvent acts as a nucleophile, you have a substitution reaction in which we formed an ether in that example. The ETO is the ether linkage. So the solvent acts as a base in elimination. If the solvent acts as a nucleophile, going after the electrophilic carbon, then you would say that that acts as a SN1 mechanism. So just as a matter of what target the solvent goes for, if the solvent goes for the beta proton, it's acting as a base. If the solvent goes for the electrophilic carbon, it's acting as a nucleophile. Substitution versus elimination. And you can see some of these things that compete. The rate of an E1 is exactly the same as the rate for an SN1, simply because the leaving group leaves. And this activation energy for the rate determining step is the loss of the leaving group. We form the intermediate, the carbocation. The more stable the carbocation, the better the leaving group, the faster the kinetics. So if I had a terrible leaving group, my activation energy would be quite high. If I did not form a tertiary carbocation, I would have a high activation energy. So things that promote E1 SN1 mechanisms is a very stable carbocation and a very good leaving group, one that would actually like to leave and be able to stabilize its negative charge. Let's practice with carbocations. What would the carbocation intermediate look like from the following alkyl chloride as it undergoes ionization? So the rate determining step says the leaving group has to leave. The leaving group is the chlorine in this particular case. So what this means is this is the alpha carbon, the carbon that is attached to the chlorine. The carbocation that forms is when the leaving group picks up its electrons and leaves. And so when I redraw this structure, this alpha carbon still has the two methyl groups there, and now this would be the positive charge. Now thinking a little bit better about the geometry there, we would have sp2, so it's trigonal planar, just to kind of envision what those bond angles really look like. They would become 120-degree bond angles for trigonal planar. So the positive charge is now sp2 hybridized. That's trigonal planar sp2. But remember, there's a double bond there as well. So what's very interesting about this carbocation is it's very stable, not only because it's a tertiary carbocation, but it can actually be resonance stabilized. When the resonance stabilization occurs, the pi bond can actually change places, and you could get your positive charge over here and have your resonance form on the other side. So it is resonance stabilized in addition to tertiary stabilized. And just kind of thinking what we went through, the leaving group leaves. That's what the step does, is the rate determining step. You formed an alkene where you had the carbocation. And I remember how I just rearranged to show that it really is a 120-degree bond angle. So I was just trying to show the trigonal planar molecular geometry, and that carbocation here is a tertiary carbocation, very, very stable. So this is a very good predictor of SN1 mechanism or an E1 mechanism. But we also mentioned that because this positive charge can be distributed across a pi bond, that it exhibits resonance. It meets the criteria of resonance structures as well. The pi bond can be delocalized, moving the positive charge to the terminal carbon and placing the pi bond between carbon 2 and 3. Resonance stabilized. Both of these conditions very much promote unimolecular reactions. So based on the stability of the carbocation is very stabilized. So the carbocation stability is very high, which gives you an indication that E1, SN1 is very likely as a mechanism. And here's some example homework questions, drawing the carbocation that would result. Alrighty, so recognize where the alpha carbon is. The alpha carbon is the carbon that's attached to the leaving group. And when the leaving group leaves, it takes its electrons with it. And so the bromide forms, that's the anion, and a cation forms as well. The cation is where the electron deficient carbon is. I'd have too many bonds there. Here's the alpha carbon, and it still has 2 carbons attached, and therefore the positive charge lies right here. That's not a double bond. So the alpha carbon is attached to 1, 2, 3 other carbons. The alpha carbon, 1, 2, 3 other carbons. So we have a tertiary carbocation. Very stable, very much promotes a unimolecular mechanism, because when the leaving group leaves, the tertiary carbocation can help stabilize the positive charge on the alpha carbon. Bromide is a good leaving group, and so that's also promoting a unimolecular reaction. Bromide is the conjugate base of a strong acid. It can stabilize the negative charge. Here is the alpha carbon in our letter B, right here, highlighted in green. When the leaving group leaves, it picks up its electrons and off it goes. So the anion that forms is the chloride, loss of a leaving group, and the positive charge, then still on the alpha carbon, still connected here as a tertiary alkyl halide. The alpha carbon, that's a positive sign, there's the carbocation. 1, 2, 3 bonds, that's a tertiary carbocation, which is also a very stable configuration, which would promote SN1, E1 mechanisms. Again, I'll highlight in green the alpha carbon, the carbon that's attached to the leaving group. The leaving group leaves, picks up its electrons, and the negative ion that forms is iodide. Iodide is the best leaving group. It's the largest halogen. It can very much stabilize those negative charge over a great surface area. It's very polarizable. So that's a very good leaving group. And when it leaves, the carbocation that forms is right there. And again, that's a nice tertiary carbocation, a very stable configuration, again, promoting unimolecular E1, SN1 reactions. Have a good leaving group. We do. Have a tertiary carbocation form. We did. Those very much are the triggers to let you know that unimolecular mechanisms will be favored. When we consider nucleophilic substitution, unimolecular, and elimination reactions unimolecular, we also need to consider the role of the solvent. And remember, the solvent acts as the nucleophile for a substitution, and it acts as the base in the elimination. So the selection of the solvent is critical. In order to promote unimolecular reactions, we want to use a polar protic solvent. Polar protic solvents make weak bases and weak nucleophiles, which then promote the E1 mechanism. Remember, strong nucleophiles, strong bases would promote bimolecular collisions. To promote unimolecular reactions, we use a weak base, weak nucleophile, and polar protic solvents meet both of those criteria. For example, here's a water molecule, HOH. It's a protonated structure. It's polar with a proton on the electronegative element. Methanol has a proton attached to an electronegative element. Same with ethanol. The proton is on the electronegative element. Those are all protonated solvents. Acetone, even though it still has hydrogens, they're non-polar bonds on the carbon, so it's an aprotic solvent. Oh, it's still polar, but there's no hydrogen on the electronegative element. These, of course, would promote SN2 E2 reactions, polar aprotic. Polar protic promote E1 E2. E1 SN1 reactions. So the selection of your solvent is critical for E1 because that actually becomes the nucleophile. And for substitution, whatever solvent you put in is going to sub out for whatever halogen you started with. Think about what I just said. Here is a tertiary alkyl halide, right here, tertiary alkyl halide. In an SN1 mechanism, if I select water, I'm going to turn this into an alcohol. If I select as my solvent methanol, I'm going to create an ether linkage, 1 carbon long. If I select ethanol, my substitution reaction will produce an ether linkage with 2 carbons after. So selection of your solvent is critical when you're looking to produce a certain target molecule. You want to make sure you're adding on the correct functional group, and that comes directly from the solvent. So for SN2 reactions, polar aprotic. For SN1 reactions, polar protic solvents are best. And SN1 E1 reactions, remember that these are the nucleophiles or the bases directly, and that process is known as solvolysis. Of course, we said the better the leaving group, the faster the kinetics as well. And remember how we determined a better leaving group has the ability to stabilize the negative charge after the leaving group leaves. And we said fluorine is a terrible leaving group because it's so small, it has a very difficult time stabilizing a negative charge. The iodide is a great leaving group because it's a very large atom that can help to stabilize the negative charge. Chloride, bromide, and iodide are all considered good leaving groups. Fluorine is not. So the second consideration is the substrate itself. Remember that we want to have a stabilized carbocation. We said a tertiary carbocation promotes SN1 E1 reactions. A benzylic carbocation, because this is resonance stabilized, would promote SN1 E1 reactions. And the allylic carbocation is a great choice for E1 SN1 mechanisms because it is also resonance stabilized. You could see that the pi bond could move and you could form a resonance stabilized structure. So those are the promotions of E1 SN1 reactions. So let's consider, the substrate, which is our alkyl halide. You want to be able to judge whether or not the halide will undergo solvolysis. In general, primary and secondary alkyl halides will undergo solvolysis only if a rearrangement is possible to create a carbocation intermediate. Here is a secondary alkyl halide. We have a weak nucleophile, water, it's protonated, so this is solvolysis, where the solvent is acting as the nucleophile itself. Think of water as HOH. And so when you think of the mechanism, the oxygen has to be able to target the carbocation, the alpha carbon that forms. And so is a secondary alkyl halide very, that's what you would think of as a secondary alkyl halide. Well, this still works because this resonance form helps to stabilize the positive charge. And so, yes, I would predict a unimolecular reaction would be fine with this case, even though this is secondary. It's sitting next to an aromatic ring, and therefore that positive charge can be stabilized through the delocalized electrons of the benzene ring. So we would have both SN1 and E1 reactions occur. Now let's focus on that for a minute. Notice that there's 3 hydrogens here in the beta position, but there's no hydrogens there. So there's only one possible elimination product that's between those 2 carbons. Those are the considerations as we practice in this lecture together. How to predict products of SN1, E1. Oftentimes they're competing reactions and we see both products with little ability to control one over the other. So let's take a moment to practice. Identify which is expected to undergo solvolysis more rapidly. So I want you to think about this term, solvolysis. What you're saying is that you're promoting a unimolecular reaction where the nucleophile or the base, depending on if you're substituting or eliminating, acts as the actual nucleophile or the base. The solvolysis means the nucleophile is the solvent or the base is the solvent. And so right now they're saying the solvent is water, HOH. We need to understand that unimolecular produces a carbocation intermediate. So what you're really being asked here is who has the more stable carbocation. That's the ultimate question. Which one the more stable carbocation? Here is my alpha carbon. The carbocation is right next door to a benzene ring. So the carbocation would be resonance stabilized. This is also a tertiary carbocation, but it does not exhibit resonance. So this structure with its resonance stabilized and tertiary would be the more, the rapidly occurring reaction. Here's the alpha carbon. When the carbon forms a carbon cation, we would just kind of consider drawing this as a positive sign here or a positive sign here. Of course, you would see that this would be resonance stabilized in the allylic position, and so this would promote faster kinetics. And here, everything is identical except the leaving group. So a chlorine versus a bromine, who's the better leaving group? And we'd say bromine because it's the larger atom, and it can therefore stabilize the negative charge on a larger surface area than the smaller chlorine. So considering resonance and considering the strength of the leaving group helps us to determine the rate of a unimolecular reaction. 2 things will promote it. The leaving group has to be able to leave and stabilize the negative charge. The second thing, when the leaving group leaves, the carbocation has to be able to stabilize the positive charge. Those 2 are very favorable in determining SN1, E1 mechanisms. Draw the expected products of the following solvolysis. When you see solvolysis, I want you to think unimolecular reactions where the nucleophile for substitution or the base in the elimination are the solvent. And the solvent here is methanol. So just think what that means. It's CH3OH. That's methanol sitting on top of the arrow. So thinking about just going through the process, step number 1, the leaving group leaves. So minus Br, the leaving group leaves. And when it does so, we form a carbocation, and that is going to be resonance stabilized. So there's our first step, forming the carbocation. In the next step, we take a look at that methanol and just thinking about what it stands for, MEOH, methanol. The oxygen is the electron-rich area, and it's going to reach out, and if it acts as a nucleophile, we'll have a substitution reaction. So if it's a nucleophile, SN1, the nucleophile means that it's seeking the electrophilic carbon. And when it does so, the substitution then forms this product. Notice here, we would now still have those two methyl groups, but we have an oxygen that's still protonated, and there's your Me, the methyl group from the methanol. Now this would have a positive formal charge, an oxonium ion, which is not the most stable configuration for that oxygen. Notice that it has a positive formal charge. So we need a next step to deprotonate that ether linkage. And that's the second step of the methanol. And I'll just rewrite that as MEOH, the methanol. And again, what you're looking now is taking the oxygen and it's going to go for this proton, and that bond collapses to make another set of dots. And finally, my substitution reaction will show the carbon leading out still to two methyl groups. And now I have an ether linkage. I have to redraw. I just didn't give myself enough room to squeeze that in. So I'm going to give myself a room down here. So I'll have my benzene ring. There's the carbon. That's the alpha carbon. It's still leading to two other carbons. And now we have an ether linkage where that's the methanol, Me, just writing out CH3 for Me, methanol. And so we formed an ether in a substitution reaction. This was SN1 mechanism. Now let's consider going back to the carbocation, going in this direction. Instead of having the MEOH act as a nucleophile, seeking an electrophilic carbon, let's put MEOH on the arrow and have it act as a base, seeking a beta proton. So here's our benzene ring. Here's the carbocation. Notice here, the carbocation, there are two equivalent beta hydrogen positions. These are both the same in terms of positions. Those are 6 equally lovely beta protons. Alrighty, they are not different from each other. So this time when the methoxide, or the methanol here, reaches out for a beta proton, that bond then collapses and you form the elimination product. Here's the beta carbon leading out to that carbon now with a double bond leading out to this carbon, and we ended up with this particular alkene as the elimination product of that reaction. So two competing reactions. Here is the elimination product. Here is the substitution product, and both would be formed. Like we saw with E2 eliminations, it's possible for E1 elimination to yield more than one regioisomer. Let's take a look at this example. E1 reactions will always give the most stable alkene as the major, which is usually the trans configuration, and the cis as the least stable or the minor product. E1 reactions are regioselective, but we cannot control the regioselectivity like we can with E2 reactions. Remember that we had Zaitsev and Hoffman, and we could say, given a primary alkyl halide, we would have a Zaitsev yield. Giving a tertiary alkyl halide, and we would promote Hoffman yield. That's not the same thing here because we're forming a carbocation intermediate and we don't have to worry about collisions. The leaving group just has to leave. So here we have an alpha carbon, and I have two equal positions here. Those two are equal, so why don't I make those the same color so I can see those two beta carbons are built the same. And I'll make this guy the beta position, which is different. So I have two possible products. An elimination reaction and a substitution. At this point, we see that they're all coming out together, that we have a mixture of these reactions. Very hard to control E1 and SN1 and just have one over the other. Notice what we have on the arrow. We have a protonated polar solvent. When I see that, I know that I'm promoting E1 SN1 mechanism with a tertiary alkyl halide and a polar protic solvent. Think E1 SN1 mechanism. One of the possible eliminations occurs between carbon 1 and 2, and the second elimination would be between carbon 2 and 3. Those are a mixture. However, the more substituted alkene, which is more stable, which would be the major product, this would be a minor product. And of course, the substitution, notice that water ultimately turned into an alcohol through the substitution process. Think about how that happens. We form a carbocation intermediate. The water is acting as the nucleophile, so it attacks the electrophilic carbon. Then you'll see that you have a protonated alcohol on that position. The water then plays a role in deprotonating that, and what it does then is reaches out for the hydrogen, and then of course that bond collapses, gives a set of dots, and that's how you ended up with a hydroxyl group, creating an alcohol functional group. So a stepwise fashion to turn a chloride, alkyl halide, into an alcohol using water as your nucleophile, your solvent. So the major product in that reaction is the most substituted, which is the E isomer. You also can create the Z isomer and a disubstituted alkene. Here is an alpha carbon that has, if you just see how many unique positions, there's one, and then of course these two are the same position. So since I think about looking at that, this double bond came from this beta hydrogen. I see that. These two positions are equivalent, so I'll just focus on, let's say, the right-hand side. I have an opportunity to have a cis-trans conformation, or better would be the E and the Z isomer. Here's the two carbons in the double bond. The priority lies on the opposite side. That's the E configuration. Here's the two carbons in the double bond. This time the priorities lie on the same side. That's the Z isomer. Here is the E, here is the Z, and of course the least stable is the di-substituted, but all indeed are made. It's just that this would be the major product, this would be a minor, this would be even less, and of course you have your substitution product as well, and that turns your alkyl halide into an alcohol through that mechanism known as SN1. A mixture of all of these is unavoidable. All will be present, not necessarily in the same amount, but they all can be isolated as part of your reaction. Let's compare SN1 mechanism to an SN2 mechanism for stereoselectivity. The first rate determining step is the leaving group leaves. The rate determining step, the leaving group leaves. And when it does so, it forms a trigonal planar sp2 hybridized carbon. This is trigonal planar. It's lying flat on the table. Now you think about holding this up, you have a pi orbital here and an available orbital here. Both are available on either side of the carbon. So when the nucleophile attacks, it can do so from either side of the carbon. So it's like a free open spot, top or bottom. So let's say if this is left and this is right, you could have the nucleophile attached from the left side, or you can have the nucleophile attached from the right side, that they are both possible. Since we have a carbocation in trigonal planar configuration, we will always lead to a racemic mixture at any chiral carbon center. Now let's remember SN2, a bimolecular collision. If we have an alkyl halide, such as a carbon leading out to a methyl, leading out to a pyridine PR and leading out to ET, and in the same plane is BR. So this is my leaving group. My leaving group has the job of leaving, right? That's what it needs to do. But in a SN2, it's a bimolecular collision. So the nucleophile must attack in the same plane on the opposite side of the leaving group. So think about how we drew the transition state. The bonds are breaking to the leaving group. At the same time, bonds are forming to our nucleophile. And then thinking just about stereochemistry, you would have the other three groups. So here could be your, what they're calling PR, pyridine. Over here would be your ethyl, and up here would be your methyl. But notice that in the same plane, the nucleophile must attack the carbon in the same plane as the bromine. And we just said this was 100% inversion of configuration all the time. That an R will turn to an S, or an S will turn to an R, 100% of the time inversion of configuration at a chiral carbon. Because there was only one side it could attack, the opposite side of the leaving group. But now in an SN1 reaction, the leaving group leaves. And if the leaving group leaves, we have an equal opportunity for top or bottom configuration. And because that trigonal planar allows you to attack from the bottom or the top, or you could think about left or right, you could have inversion and retention, leading to a racemic mixture of the chiral center. Now, practically speaking, oftentimes it's not an even 50-50 split, because opposite charges attract. If there's the carbocation and this is the leaving group, notice that opposite charges may still be close in contact with each other. If this bromine is near enough to the carbocation, it may be preventing an attack from that side. If there's a great distance between the carbocation and the bromide, I would then predict more of an equal racemic mixture. So really, depending upon the distance between the leaving group and the carbocation, you might actually see, if the bromide is still staying close to that carbocation, if it's lying close, it's inhibiting this particular attack. And so you could find less than 50% of that configuration and maybe a little bit greater of this configuration where there's no unhindered attack is available there. So just something to consider about carbocation intermediates. All right, well, let's take a moment and just kind of process, give you some think time. You might even want to just pause and think. Draw all the expected products for each of the following solvolysis reactions. I gave 2 examples from your homework. I would encourage you to stop and think, try drawing out these, and then come back when ready to check. If you can hear the pounding, we're finishing the basement downstairs. Okay, well, let's see that you're back. So step number 1 in letter A, the leaving group leaves. And when it does so, it forms a tertiary carbocation. Now, I always like to have the carbocation, and I just want to make sure that if I have to predict shifts, I want to do so right away and before I go on and start to draw products. And what I mean by a shift is, do we have a hydride shift or a methyl shift, something where I have to make sure we turn a secondary into a tertiary carbocation if possible. So we had 2 instances that we considered a hydride or a methyl shift. But I don't see that needed here because I formed a tertiary carbocation. So the answer to that is no. The carbocation is stabilized. There will be no shifting of the positive charge between a hydrogen group or a nearby methyl group. Then on the arrow, I see ETOH. This is a solvolysis then. That means that the nucleophile for a substitution will come from the ETOH. If this acts as a nucleophile, it will seek the electrophilic carbon. And so let's just say in that direction, we're going to say substitution, because I have the ETOH seeking out the electrophile. And when that occurs, the ETOH is now connected, but still protonated. So in the next step, so step 1, the leaving group leaves. Step 2, the carbocation is an electrophilic center, and so the solvolysis occurs as a nucleophilic attack on that electrophilic carbon. We then just need to deprotonate, and the solvolysis occurs again where the solvent now is going to abstract the proton to deprotonate, and we form OET. Now think about what that means. You've got an ethyl group. That's what ET is an ethyl group. You have now created an ether linkage. Alrighty. Now, when I look at this, this is an achiral center. It has 2 exact groups. To be chiral, you have to have 4 unique linkages. Since it's achiral, I don't have to consider dashes and wedges. What about the elimination? Let's go this direction and treat this as an elimination reaction. So ETOH now is going to act as a base. And as a base, we need to find the beta hydrogens. The beta hydrogens occur, I can see, in a position here and here, but those are equivalent, and I can see them here. So I'll have 2 unique eliminations. Here I would have the least substituted elimination, and I would have the most substituted elimination. And I would see that those are major and minor. But there are indeed 3 separate products. We have 2 products from the elimination. We have 1 product from the substitution. The substitution only gave 1 product.
Continuing our work in chapters.
That was another video. It only has 1 product in terms of stereochemistry because it's an achiral center. Otherwise, we could have a second product for substitution if it were a chiral center. We'd have to have an R and an S configuration. Let's take a peek at B. And again, I'll work as many practices as you'd like me to. Otherwise, fast forward if you have this down. But more practice, the better, I think. Here we have a tertiary alkyl halide. And the first step is the same in both directions. So the same first step, the leaving group leaves. So in that particular step, we form a carbocation. And at this point, the carbocation is tertiary. So I would not have any rearrangements. But I'll keep stressing that because if there is an opportunity to create a more stable carbocation, right now is the time to do it. So minus the leaving group. Leaving group leaves, step number 1, the rate determining step. Then I have a carbocation intermediate. Carbocations then can either undergo E1 or they can undergo SN1 mechanisms. On the arrow sat water, H2O. So that means water is going to act as a nucleophile in an SN1 reaction. The nucleophile seeks the electrophilic carbon. So the first attachment is the water attaching to the electrophilic carbon. Of course, this is a positive formal charge, an unstable oxonium ion. So in the next step, the water will deprotonate the water molecule to go on and form the alcohol. Now with this example, the OH is formed. And do we have to consider stereochemistry? The answer is no, because this is also an achiral carbon, because there is no point of difference on that cyclic structure. So as I continue around there, I have equivalent carbons here, and I end up with equivalent carbons here, and therefore I do not have 4 unique carbons. So that is an achiral center. I do not have to consider stereochemistry then, I just produce an alcohol. How about the E1 mechanism? I had this tertiary carbocation. If now the water acts as a base, so SN1, it's a nucleophile, E1, it's a base. And that means it's going to go for any beta hydrogens. Locate the beta hydrogens. I have 1 set here, and I have 2 equivalent sets here. Those are identical. So I can see 2 unique alkenes forming. One of the alkenes will be di-substituted, and the other alkene will be tri-substituted. And of course, we would predict the major product being the tri-substituted alkene, and the di-substituted would end up to be a minor product. But again, all of those are in the products, right? They're all in a mixture. So you have 3 unique products. 1 of them by substitution, 2 of them by elimination. If indeed we had a chiral carbon form, the substitution could give us a racemic mixture. So we could see a possibility of 2 different products from substitution if indeed we had a chiral carbon. We have not in these 2 examples. How do we learn about all these mechanisms? Sometimes it seems so abstract. How does a chemist go about figuring out mechanisms of substitution and eliminations? It says you should learn to appreciate how we've come to know all of the mechanisms. And one of the ways that we study is through isotopic kinetics. In other words, we take a hydrogen and replace it with one of its isotope, deuterium. Now remember, hydrogen, the most common form, is hydrogen 1/1, where the mass number and the atomic number would tell us that this has 1 proton and 0 neutrons. There is a second isotope of hydrogen. It's hydrogen 2, called deuterium. Hydrogen 2 tells me this has 1 proton and it has 1 neutron to give me a total mass of 2. It's a heavier hydrogen. Now, just because it's heavier, has a neutron with it, it does not change the chemical reactivity. It does everything exactly the same as what's called proton there, the hydrogen 1. It's just that it's a little heavier and therefore we can track it. So consider the following reaction when we have an alkyl halide undergoing elimination with the strong base. You already know this will promote an E2 reaction. This is a primary alkyl halide, and we have the presence of a strong base. Both of those are favoring a bimolecular collision. The beta has 2 hydrogens, and so you can see that the alkyl halide, when it eliminates a hydrogen, that bond collapses and the leaving group leaves, you form an alkene. You form the conjugate acid of your base, and there's the leaving group as it left. Now, instead of having 2 hydrogens here that are just H1, let's put a deuterium here, H2. So when you see the letter D, just think of it as a proton, but I can track it because it's a heavy proton. It's got a neutron with it. What we notice is that when we look at this reaction, the base still goes after the beta hydrogen, forming the alkene, the conjugate acid of the base, and the leaving group. But this reaction was actually slower. And when you study kinetic isotope effects and measure the rates of reactions, deuterium is often used to indicate if the hydrogen is actually part of the mechanism. If you replace a hydrogen with the deuterium and the kinetics change, now you know that this is part of the mechanism. If you put on a deuterium and there was no effect in the rate determining step, well, then you know that hydrogen was not involved in the rate determining step. We've studied this to find that when you replace hydrogen with deuterium, the beta deuteriums instead of beta hydrogens, it actually occurs 7 times slower. Therefore, you know that this is a concerted elimination where the deuterium is part of the mechanism. So really just giving us insight into how we study reaction mechanisms. We often substitute isotopes in and track the kinetics and see how it's affected. So here's an example where we place some hydrogens with deuteriums. Notice that this is just like carbon H3, carbon H3, carbon H3. So this is the exact same structure. It's just one has deuterium instead of hydrogens. And remember, the deuterium slows down the reaction. So which one would go more rapidly? Identify which one is expected to go under elimination more rapidly. Well, the true protons would. And here, notice in the next one, here is the alpha carbon attached to deuterium here. And now these are actually hydrogens that are just CH3s. Those are normal hydrogens. This has no effect because it's not a beta hydrogen. So again, this one would go faster, and just tell yourself, when the reaction above, when deuterium is replaced, it slows down the reaction. So if you are replacing hydrogens with deuterium, that would be slower. This one would be slower, and the faster the reaction would have pure hydrogens. Now, I've been talking quite a bit. It's been about what? Oh, over an hour again. So I'm going to pause the video here, and when we come back, we'll have some final thoughts on Chapter 7. We'll wrap up our final thoughts, a couple last sections and example problems. And again, this is a very difficult chapter. The repetition is important. Come back when you've rested.